All right, let's get right into it. Today, we're unpacking a truly incredible explainer that looks at a radical re engineering of the AI tech stack. Typically, when we talk about large language models and transformers, we're just swimming in a sea of messy floating point math. But today, we're looking at a system that totally replaces that continuous, imprecise math with a single, elegant mathematical object. It's called the prime power transformer, and it's fundamentally changing how we think about compute, literally from the physical silicon all the way up to distributed network routing.
Before we really get in the weeds, I want to anchor us with a profound principle drawn directly from the source material. The system gets simpler as you understand it more, not more complex. Keep that in mind because that's our guiding star for this explainer. The goal today is radical simplification. We aren't just bolting on new compression tricks or adding more layers of abstraction. We're going down to the absolute foundation of how neural networks calculate and finding a much cleaner, mathematically unified way to do it. So here's our roadmap for the journey. First, the exact arithmetic substrate. Second, negacyclic rings for attention. Third, zero-copy hexagon DMA. Fourth, the prime-factored lattice. And finally, 6 layers, 1 object. The exact arithmetic substrate. Now, what's really interesting here is the specific choice of numbers. We're looking at an imaginary quadratic field, specifically using the discriminant -163. Now, why 163? Well, because it's the largest of the Heegner discriminants, with a class number of exactly 1. And in practical terms, that means its ring of integers forms a unique factorization domain. Every single element factors uniquely. By using this exact arithmetic substrate, every linear algebraic step of inference in the transformer gets an exact, invertible representation in integers. No approximations, no rounding errors. To really get why this is a game changer, think about standard floating point arithmetic. It's non-associative, non-commutative, and crucially, it suffers from drift, especially when you quantize models down to lower bit rates. The numbers just lack any underlying algebraic structure that the network can exploit. But with the prime power transformer's exact integer arithmetic, zero drift. It's perfectly associative, and because of a property known as Frobenius cancellation, the scale factor perfectly commutes through the attention dot product and completely vanishes at every normalization step. This guarantees bit-identical output to an unquantized reference. For low-bit inference, that physical payoff is just massive. And just to prove this isn't some theoretical math trick, a complete 13-step exact substitution table was actually built. Just to highlight a few. Step 1, standard embedding lookups are completely replaced by a combinatorial Mobius reconstruction over square-free token indices. In step 6, the standard softmax, that becomes a p-adic exponential on integers. And for step 9, the feed-forward network cold start utilizes Euler's famous prime-generating polynomial, n squared plus n plus 41. This guarantees perfectly distinct primitive activation indices for the first 40 tokens. I mean, we're talking about a full architecture replacement here, ground up. Moving right along, section 2, negacyclic rings for attention. So in a standard transformer, attention is a real valued bilinear form, right? Well, not anymore. Here, it is entirely replaced by a negacyclic cyclotomic ring. Queries and keys get encoded as polynomials using a CKKS-style encoder, and because we're taking the quotient by x to the power of n plus 1, the ring is negacyclic. All that means is when you multiply the polynomials, the coefficients wrap around with a sign flip. This specific algebraic structure becomes your direct replacement for the softmax attention kernel. So, why is this mathematical shift so powerful? Well, because the ring is negacyclic, it actually lets us diagonalize the multiplication using a number-theoretic transform, or NTT. This alone slashes the computational cost of attention from an n-squared scalar dot product down to an n log n polynomial multiplication. And the absolute best part? It is perfectly accurate. The theorem of KL0 equivalence guarantees that for head dimensions up to 256, this polynomial ring path is mathematically equivalent to the floating point softmax down to the exact unit in the last place. Massively faster without losing an ounce of precision. And the real-world impact of this is just wild. When you implement this math natively, the persistent NTT domain caching delivers a 9.78x compression of the key-value cache on hexagon hardware at a head dimension of 128. That's nearly a 10-fold reduction in memory footprint purely by keeping the math in the correct algebraic domain. This is absolutely huge because shrinking caches by 10x is exactly the secret sauce that lets us run massive models locally on edge devices, like your phone, without instantly burning through all its memory.
Section 3. Zero-copy hexagon DMA. Usually, moving data from the host CPU over to the Hexagon DSP involves really slow Marshall heap copies. You have to allocate memory per call, copy all the data over, and free it. It's a huge bottleneck. The Prime Power Transformer completely sidesteps this using zero-copy DMA. It uses Shared Memory Management Unit, or SMMU, DMA buffer pools via the RPCMM alloc function. So the memory is pre-mapped on the DSP side. The payload just lives in the DMA buffer, which means there is zero host side allocation happening during the dialog loop. The zero-copy benchmarks backing this up are super rigorous. By running 1 megabyte ping tests, comparing those old standard heap copies directly against direct memory access, they confirmed a sub-millisecond inference hot path. But, and this is a big but, you absolutely have to maintain strict hardware discipline here. The allocation size you request has to perfectly match the expected interface definition language, or IDL, length. Even if you're off by just 1 byte, say you add a safety pad to your buffer, it triggers a totally silent AEE unsupported failure that masquerades as a DSP crash. So it's precision hardware engineering that's perfectly complementing that precision mathematics we talked about.
All right, section 4, the prime factored lattice.
Let's zoom out a bit and look at how knowledge is actually passed across the network. This math compresses semantic information into a tiny, mathematically rigid format called the 63-byte spinner block. It packs exactly 504 bits, 8 square-free anchor coefficients, 55 residual coefficients, and your global scale and sign. It is information theoretically tight. We are talking right up against the Haza whale bound for channel capacity. And get this. Because it's exactly 63 bytes, if you add a 1-byte sentinel, it perfectly fills a standard 64-byte ZMM CPU register. Just a beautiful structural coincidence. This layout is frozen, so network transfers become incredibly lightweight, perfectly idempotent, and entirely deterministic.
So how does this all build the network layer? Well, the network utilizes a 2-axis Fibonacci prime address space for its distributed hash table. Step 1 is the semantic axis. Since data is encoded as prime factored trees, the content naturally clusters together. Slabs with the same prime root hold semantically similar content. Step 2 is the load axis. To keep popular nodes from getting totally overwhelmed, the node addresses are multiplied by the golden ratio, Fibonacci hashing, which natively balances the traffic. This actually solves the standard Cadelmia clustering problem, which is a classic headache in distributed P2P networks without ever having to rely on expensive cryptographic hashing. Section 5. 6 layers, 1 object.
This perfectly synthesizes the core theme of the prime power transformer. Listen, there is exactly one mathematical object here, a discrete lattice over a cyclotomic ring, but it manifests across 6 distinct architectural layers. Down at the silicon layer, it dictates vector width and 30-bit integer precision. Up at the kernel layer, it acts as the Fronius row scale and the mapmul. Over at the cache layer, it projects key values right onto those tiny 63-byte lattice anchors. In the model layer, it's the polynomial multiplication replacing softmax. Scaling out to the sieve layer, it organizes cached cells. And finally, at the network layer, it forms the prime factorization DHT routing key space. It's the exact same discrete lattice mass scaling flawlessly from a microscopic ALU to a global network.
Which leaves us with a truly fascinating question to ponder as we wrap up. If replacing imprecise, bolted-together floating-point math with a single, elegant, prime-factored lattice can simultaneously fix inference drift, accelerate attention, shrink caches by 10 times, and perfectly route distributed network traffic, what other hardware bottlenecks could we entirely erase by unifying our mathematical substrates? Thank you so much for joining me on this explainer today. I really hope this sparks some fresh ideas about the future of hardware-software co-design. Catch you next time.